Dear everyone, today we would like to continue our operation guide related to the RG Raman microscope, and together with Andrei, who actually responsible for the software development called MiraSpec at our company, we will show you how to operate the microscope using MiraSpec software. In a previous video, we already explained how to download software from our website, where you can go, register and download it. Today, we expect that you already have it on your computer. And the first step, double-click on MiraSpec and it's loading. Let's expand the interface. Before pressing connect, if you didn't set the proper configuration, for example, in configurations we have RG Raman microscope, mini Raman, spectrometers and so on. We should select RG Raman microscope. Currently we have installed 532 RG spectrometer, this one. But it has been already pre-selected. Nevertheless, that's where you change settings if you change module installed inside. Then we press connect and wait a little bit until everything is connected. We already can see that microscopy stages has been connected. X, Y, Z is ready. We can see that there is a temperature and humidity inside the RG microscope is monitoring. Nevertheless, we still wait for connection for the spectrometer, and we do not recommend to press any buttons until this one is active. You see now COM25 serial number of the spectrometer is there, and now it's ready for operation. Before doing any manipulations with the sample, turning on the laser, we would like to step by step go through the menu, and let's do it one by one. File, spectroscopy, visible microscopy, Raman mapping, view and help. Those are the options we have here. If there is a file, we have option to save the spectrum which was captured, and you see it here on the screen. There is also connection window which you can see here, and exit which is equivalent to close the software. Then spectroscopy. Here we have many settings. Acquisition parameters, let's say advanced settings. That is something which is most likely needed for service and for advanced users if you want yourself to improve calibration, improve laser limits, threshold stability and so on. We can touch that in a specially dedicated video for that. Typically you don't need that. Laser parameters, they are here. Here you can turn on the laser, control its power, acquisition, number of repetitions and so on. Then also wave number range. If I select this option, menu will appear, for example, here, and you can change the wave number range you would like to see. Nevertheless, for this specific spectrometer 532 RG, you can start working from 15 inverse centimeter and end at around 4000 inverse centimeters, and those are the numbers pre-selected from the configuration file, recommended numbers. But you can change if you wish. Then we can go in plots. We can plot Raman spectrum, and here would be Raman intensity and Raman shift. You can also select wavelengths. If that option is available, window appeared here, and we can place it in this window and merge with the rest of the windows. You will see nanometers instead of Raman shift. But typically for Raman measurements, Raman shift as a horizontal scale is more preferable. What else do we have? Pre-processing, smoothing, baseline correction, background correction, transmittance correction. All of those features is already opened and you can see them here. Smoothing can be done using Savitsky Golay. If you select that, you can select the radius and polynomial order. Radius, it's a window how many pixels nearby you use for interpolation between those. And also asymmetrical least squares. Here, the larger the number, lambda, the more smooth your spectrum is. So you can use this or that one. We applied here the most popular algorithms in Raman. Baseline correction, it is typically used as post-processing to correct your Raman background. Rolling circle or
Asymmetrical least squares based
on PLS, on partial least squares, yes?
no, asymmetrically reweighted penalized least squares.
Asymmetrically
Reweighted
reweighted penalized least squares. So this is another option to correct background with even 3 parameters to play with.
It's more advanced technique. So there are 3 tuning parameters. So you need to play with them to obtain a reliable result.
Yes, and sometimes it works really great, but it requires a little bit more practice with it.
Yes.
Rolling circle is simple. You simply select the radius of the rolling circle and it will work. Then background correction, it is something which is very useful if, for example, your Raman probe has certain background and you want to compensate on that. Or you want to compensate on environmental contribution to your Raman spectrum, which you measure without sample being in place or without laser being turned on. And then it will be automatically subtracted. Useful feature. And transmittance correction, this is something to correct the homogeneity of your throughput of your Raman system. It is quite advanced tool which we also would like to focus on this particular option in a separate video. Nevertheless, we discussed spectroscopy, pre-processing. Then there is also data analysis. Data analysis window, if you click on it, it will appear and it will look like that. All measured spectra, they will be shown here. And you can open spectra. Let's open something. For example, here we have a lot of spectra of methanol in water ethanol solution, I guess. You see, we open the spectra, they appear here. And we can do smoothing, background correction, and normalization. Let's say before any manipulations, normalization could be useful. Normalization options are multiple. Andrei, could you briefly explain differences between this?
This core normalization means that each spectrum subtracted with its mean value and divided by its standard deviation. So the resulted spectrum will have the mean 0 and standard deviation which equals to 1. Mean normalization means that we just subtract mean spectra value from the whole spectra. Min max, we subtract minimal value and divide by maximal value. Unit norm, the whole spectrum divided by its L1 norm or L2 norm in the case of unit norm L2. And yeah.
What would you recommend for this data set? Probably L1?
Yes, L1 is a nice choice, but if we have some unwanted background, this score is preferable. But in the case of this score, the resulted spectra may contain negative values, which
I see. And
is undesirable for some cases. But for scaling, it is a good option.
Nice.
So you can play with them and choose the proper option which fits your particular case.
Okay, then L1. Oh, and now they all normalized, and we can even see the isosbestic point here, which is a nice starting point. This is a data set of different concentration of methanol in water ethanol solution measured by mini Raman with 660 nanometers laser. And let's see what other options we have to play with the spectra. Analysis, PCA,
non-negative matrix factorization, or multivariate co-resolution, in other words.
And calibration if you want to quantify something. I would say PCA and an NMF would be a good choice for mapping or data set where you can see the image and you can do chemical imaging instead. But of course it can be applied for any kind of perturbation in your spectral data set. We can maybe explore a calibration. Let's say if we have this data set and probably data is loaded, now we need to apply values for calibration.
Yeah, we need to assign
water, methanol
values.
0.1%, methanol 0.5%, unknown constant 0 again. Let's skip it. Can we skip it? Yes. We skip.
If we do not want to
1%.
include spectrum in our calibration set, we can just keep it.
And we can use one of them as prediction, yes? Or several of them.
Yes, yes.
So 40, 60, 80. Nice. Let's say all calibration.
Just to show, before calibration you also should choose maximal principal components to include.
Yes, so
you should press, for example, 10 and
a lot.
Yes, and the algorithm will indicate the best number of components you can take into your calibration.
I see we have few.
Yes, it is partially square regression or principal component regression. So the most popular is PLS regression, so we will use it.
Okay.
And data
center?
Yes, should be centered.
According to, with regard to
for scaling, to minimize some bias. It is it will have some different features. It is usually the data mean centered.
I already want to press calibration.
Yes.
Should I?
Yes.
Good. Okay.
And you see the best calibration is obtained for 5 principal components.
I see.
You can switch the number of principal components and see how calibration curve look.
With 1, with 2, with 3, with 4, and then even 9 or 10, it's really not helping, just making it worse. And if I want to see this principal component number 1, the spectrum, I can actually see that.
It's regression coefficients. You can see the.
So this is component number 1. How it looks.
It is regression coefficient.
Regression coefficient. Okay. Number 2.
Yeah.
Number 3.
So including more components,
5. The rest is just noise.
Yes.
Not really informative. Okay. So we keep it as 5. And prediction results, but they are not yet ready. We can select several of them for prediction. Concentrations. Correct?
Yeah.
Whatever. This one. And prediction. Apply. And we can see they were quite well predicted.
Because
unknown concentrations.
Because this data was included into calibration set.
And I see. So we should skip them for calibration,
Yes.
right? Like that.
Yes.
We calibrate. It's not that good without those, but we're playing with it.
Yes.
And now prediction. No, but that's unknown points for the model.
Yes,
Okay, yes. And it managed somehow to do a nice, more or less accuracy. Good, but that's an option to play with. The better data you have, the more accuracy you will get. The more data, the more accuracy, and so on. Very nice. And identification also. Let's clean delete selected. Yes, there is nothing here. And even select all and delete before post-processing. Identification, maybe we can load the library first to see what we have. We can select from which laser the library was collected from our default library. We have around 200 components by default. Plastics.
What do you prefer?
Yes, and okay. And now we load it from 785, measured by mini Raman, I suppose. The spectra of multiple plastics. And what can we do with it? We can select some spectrum, clicking on it.
Clicking on top.
Here. Okay, let's say this one. And identify. And it has shown something, but quite a lot of spectra. So we can, in options, set threshold. Please show us only with the high correlation coefficient, and search again. And it found only one. So we can play with that feature and search again. Doesn't help. Maybe 85, and it will show few already. Not yet. 80. Yes, and it found several with different correlation coefficients for the rest. That's basically, if you have a known spectrum, you can identify, and I guess we have also some options.
Yes.
We can set different correlation techniques.
Yes, there are 3 correlation techniques. The most classical is Pearson correlation, linear correlation, and cosine function or square of difference cosine function. So you can play with different techniques to obtain more robust result. But as a first step, the usage of Pearson correlation is enough.
I see.
You can play also with pre-processing technique. In some cases, background elimination may help to obtain more robust results.
And I guess in the future we will try to implement here some machine learning tools, and it will be even more accurate.
Yes.
Looking forward to that. So, we have all of that. Let's clean everything. And that was spectroscopy data analysis. Visible microscopy. When we click on it, it will be shown here. So we can deselect it. And you see this window is empty. And we can select it again. And it will appear here. By the way, the same can be done by this easy intuitive menu. So I click on microscope image, and it will appear, and I can remove it like that. And if you don't like this panel, right click, disable, and it will disappear or appear again. Very nice. Inside the microscopy we have several features. I can reduce it a little bit down to show. So this is a visible image. And this is an option to turn on the LED manipulation, and you can use it. When you add light, there will be more light here. Then you can move over your sample. This is a step of 1 micron. Here you can select the step. And if you press another point, it will be 10 times longer, so 10 microns movement. Horizontal direction and vertical direction. Also the same for axial. 10 microns up, 10 microns down, and up, like that, and tiny step for 1 micron. And here you can play, and let's say if it will be 100 micron movement, I move and it moved on 100 micron, or if I play here, it will move on 1 millimeter. One direction and another direction. Then also let's remove it back to 1 micron step. We have an option to select the direct point where we would like to be. Let's say I want to be at some different depths precisely, absolute number in millimeters, and it will go there directly in X, Y, and Z positions. And if your microscopy stage is not properly recognized, you can press home and it will be calibrated. If you have doubts for some particular axis, X, Y, or Z, you can press it independently. And if you would like to start mapping from this specific point, you press here, and all the positions of X, Y, Z will be transferred in Raman mapping settings in this window. So I guess basically it is more or less everything about this window, but there are also manipulations with microscopy image. Let's try to do them one by one. Here you can add manipulator or remove it for sample movement. And this is also the ruler. So you can get here some microns. And if you don't have that, you can calibrate your image. Let's say we know that the size of polystyrene beam is 3 micron. I press this tool and I do a cross over the bead and I say it is 3 microns. Okay. And now it is calibrated. And by the way, in order to do it even more accurate, I can crop over this area and do calibration again more accurately. Let's say this one is 3 microns. It's not symmetrical crop, that's why it's a little bit extended. But if I press restore the image, it will be normal dimensions. And I guess it's already calibrated. So of course you can use longer objects for calibration and you will get more accurate dimensions, but that's how it works. Then let's say you don't know where is your laser. By the way, in order to turn on the laser, it's in spectroscopy, acquisition parameters, laser parameters, and then they appear here. You simply press on. And we have this central field of view, but you may be interested to know precisely where your laser is. In order to do that, we wait until laser is stabilized. It can take a while. Okay, now laser is stable and we see that the laser dot appeared on the screen. And we would like, for example, to know the location. So I press this tool and click on the center of the laser dot. And now we always know where the laser is, which can be useful, for example, if we move a bit on a sample, we may not be able to localize where the laser dot is, but the cross lines would always show us where it is. And in order to see the live spectrum, we press Raman, plot, right-click, fit to window, and we will see the live Raman spectrum. And if we move out from the polystyrene bits, we see only the spectrum of calcium fluoride, but not polystyrene. We back and we see polystyrene, we out, and we see calcium fluoride. But let's go routinely one by one with our tools. So this is something which is useful, we understood. We can also flip the image if it doesn't match with our movement, or we like it more intuitive. If you press right, goes left, could be. Then you can switch. And yes, basically we covered everything here. I'm not sure I lost something. Yeah, there is something could happen with your camera. For example, if I stop it, yes, you see image is frozen. Nothing changes. Then you go and press start camera, and it will reconnect the camera. And here you can deselect the device and select it again as another option to activate your camera. Now it's active again. We can change the contrast. By the way, samples are different. Right now it's a glass plate, calcium fluoride plate, and laser reflectivity is little in comparison if you will study non-transparent samples like silicon or metal sheet with sample on top. And there you may need to increase the light to have a better ratio, or decrease to see laser spot better. Yes, so it depends, something like that. Now I guess we are ready for some next step. By the way, this actually cross line may not help too much if I want precisely to see the laser spot size, so I can probably move it. It depends already on a user taste. And let's say visible microscopy, Raman mapping. Here we covered all of the visible microscopy Raman mapping settings. If I press Raman mapping settings, they will appear here. Here they are. We can extend them a bit. And we can also do it by pressing this fast menu. In order to see the Raman mapping result, there is another option. It's available here, Raman mapping viewer, or here as well. If I press it, it will appear here, and it will be active in a while when we start. Basically, we will go into detail how it works on the actual example. Then a menu, view. Add perspective. What does it mean, perspectives? Let's say we like the windows as they placed now, and I could call this perspective test 1 and OK. And then for some reason we closed the windows and they look very differently, and we don't like that. We go in view, perspectives, Alexei 1, test 1. We press on test 1, wait a little bit, and software must return to the position as you saved it as a perspective. Also you can change the layout. Now it's dark, you can do it light. It helps in my case when I show presentations on a screen to do it light. Then it inverted also the graph representation. So this sometimes works way better. However, to my taste for today's explanation, the dark layout works better. And we have some options in between. Not fully dark, but dark green, light purple, dark purple, and so on. You can clear the perspectives and you can show the console. Then help we already touched. It is if you want to change the Raman spectrometer for a different one, mini Raman spectrometer, RG Raman spectrometer with a different laser and so on, then you change the layout. Or you want to use this software for spectroscopy only, then you select here in the folder where your software is placed, here are spec and the last version, configurations. Let's say mini Raman spectrometer, and you select power dual, standard dual, SERS, and so on. And it will change the pre-configurations for your device. Good, now let's do some Raman mapping and enjoy this process. First we should start looking from which point we would like to start the mapping. And let's say I personally like this point. Before doing that, I would like to estimate that system, when we produce them, we make alignment in a way that the best visible image focus matches with the best Raman signal. But you can check that. Let's say, let's focus on the polystyrene bead, this one. Yes. Let's update the scale. and let's see that it is the maximum. I suggest to do it probably somewhere where you have more material, here for example. And let's see if it is the maximum. It's getting less when I'm getting out of focus, it's more, and it's getting less again. So really, indeed, when you have the most sharp visible image, you have the sharpest Raman signal. Good. So we verified that, and now let's do some mapping. I prefer to, for the demonstration purposes, to select the more individual bits to show that we can see them. And let's say we start from this point. I press this one button, and what will happen? Let's say before I do that, we want to do XY simple mapping. You can do XYZ mapping, XYZ time mapping, many options. X, and we transfer, Y, and we transfer it in this field. And then you have options to start, point, range, number of steps, counts, and step size in microns. And I want to start mapping from this particular point, so I press this button, and it will transfer the numbers of actual, which are shown here, the actual absolute in millimeters, and now here they transferred in micrometers. You see the units they shown here, micrometers. And the range, well, the range could be maybe around 10 to 10 micron. So this is 1 micron step. If it's a double click, it's a 10 micron, but it looks like maybe we want around 15 per 15 micron. I would say, okay, let's go here, the range 15. And I want to go down in Y. So I show here, I add here minus 15. Simply because on manipulator, when it's down, it's minus, when it's up, it's plus. The same in X. When it's to the right, it's plus, when it's to the left, it's minus. And I want to go to the right in X and to the down in Y. So plus for X, minus for Y. How many counts? Now with 11 counts, you would get 1.5 micron step. I think we want better. 300 nanometers. We can wait a little bit too long for that. 40 per 41, 41 per 41 pixel. And this would be almost 400 nanometers step. Okay, the next step, we select where we would like to save our spectrum. And it could be any location you want. Oh, basically, sorry, I actually need to select something, and usually it's data, RG Raman microscope 532, and polystyrene 50x objective, and test one. Good. By the way, yes, we have multiple adapters, and you can operate with Olympus objectives. You can operate with Zeiss, Nikon objectives. We supply different rings to match the treat size. Currently, we operate 50x Olympus microscope objective, and this is a field of view of approximately 100 per 100 microns that you can see, or maybe slightly more. Yes, it's actually more. It's approximately 200 over 100 microns, the field of view with 50x microscope objective. But it could be any, it could be 5, 10, 100, any NA you wish, and we design it in a way that system provides diffraction limited lateral resolution and axial resolution. Simply because pinhole size is approximately 1 Airy disk in the spectrometer. Let's start the mapping. So in order to do that, we select the laser 532. Yes, we can map in units in inverse centimeters or in nanometers or both. I guess today we care about centimeters. We can go zigzag mapping or one-side mapping. I suggest for high resolution, and it is high resolution, we go in nanometer scale. Do not apply zigzag, and this is turn off the laser after the mapping, but we may not need that. So let's finally start. I press start, and you can see that the laser is moving. We can actually probably even crop to see better how it is going.
The current status of mapping is represented in status bar, and
I see, yes.
Yes, it is progress, and
Mm-hmm.
elapsed time is estimated to indicate approximate time of scanning.
Yeah, as you can see, we are just at the beginning of our mapping time, but you can see how much is left. And for this type of map, 50 per 50 or 40 per 40 pixels, the time left is 11 minutes, which is probably not bad. Exposure time was 150 milliseconds per point. One repetition and approximately 20 milliwatts on the sample. Those are the conditions, and by the way, yes, all of that you can change. You can change the laser power here, the exposure time here, number of repetitions here, and the CMOS sensor gain in here. That we can actually cover just after the mapping to play with all of that. And yes, now there is probably a time to go to our Raman mapping viewer. We click simply another window, and the mapping viewer would appear. Let's decrease this window and maybe
You can just detach this window
to extend it for entire screen.
Yeah.
And sometimes that's really helpful. And now you can see that there is not much useful signal, but probably it's because we need to select the peak of polystyrene. 1001. And now something appeared, but it's noisy. And the solution for that, you can actually average this peak. And this would be the average tool. Half-whites, how many pixels in centimeters you would like to average. And now we see the result of mapping. We can wait a little bit. As you can see, one of the most interesting benefits that you can in real time explore where your laser is moving and see the Raman. And of course there is no contribution of the visible light into the Raman spectrum. How do you think having the best focus?
It looks pretty good.
I'm not so sure. Who knows? Let's wait a little bit more. So the resolution of the Raman image strongly depends on how precisely you are aligned in axial position. Almost half of the map is done. Do we have a square pixel here? Yes, now we do. I can see that our mapping is almost done. Well, there are a few things that we can do here. Well, first, as Andrei said, let's expand the map on the entire screen. And we can estimate the show right click, show trace lines, and also show cross sections. And we click here, and we can estimate the cross section. How much is it in microns? So it is in millimeters. 1 micron, another micron, so 2 microns. One, am I right, Andrei? Yes, it is 1 micron, 1 net. So, oh, sorry. Let's back to normal. 2 microns, and half maximum is around 3 microns or so. Just we know that the size of polystyrene bits is 3 microns in average. So I believe we are good in terms of resolution. By the way, you can save all of these profiles. You select the profile, right click, save selected, and it will be saved as TSV file in the place you wish. The same for the Raman spectra. You click on the Raman spectrum, you select the spectrum, save selected, and it will be saved. Also, pressing Ctrl, you can average an area and press average. And now you can see there are two spectra. The blue one, way less noisy, yes, and the red one in 1 pixel, and this is an average over the multiple pixels. So you can then select it and save the average spectrum. And there are many other options to play with here. So as we can see, our mapping is done, and now we can do some map post-processing. So several options you already saw. We can select the profiles, but we go one by one. So we can open the map, and we can export the map.
We should select, and
we should select it here and then export. And yeah, you may not like the image. It's simply because we selected it and it's not in the proper peak position. So I can select the pixel and then, let's say, zoom a little bit on the peak of polystyrene and click on this peak, and the map will appear. I can also do it in wave number. You see, I move over here and I select the proper wave number, and it's also shown. And I can also average the area over we would like to see the result, like this. And if we show the cross lines, I can move it in order to select the proper pixel in both dimensions here. And it's of course something you can play with. Let's say it could be y over wave number or x over wave number. Yes. Or here you can get the profile instead of the spectrum. The most useful way is of course xy wave number. It actually was y vertical, horizontal x, and spectra here. Okay, let's do something else. We can export in the format of the mirror spec, which is MR spectra, or in MATLAB, and it will do the hyperspectral imaging according to the MATLAB format. We can save image, which we see here, as PNG. Post-processing, we can crop the image, let's say in x, y, or wave number dimension. Let's say we don't really need the high frequency range, or not that much. Let's cut it at 3400. And low frequency, maybe we want just 770. And the y, I personally don't really like this x a little bit, so we can do it a little bit less here, for example, and less here, and press OK. And now it is cropped in multiple dimensions, and it's shown here. What else? Smoothing background correction.
These options are the same as in the data analyzer, but you should be careful to choose proper plot dimension, because it was represented spectrum by spectrum. So we need to choose the proper wave number direction. It is already a number, but you can also smooth Y slices or Y slices or X slices. It's
okay, but here we care about wave number.
Yeah.
I see. Should we try it?
Why not?
Why not? Rolling circle, enable, and OK.
Yes.
And it takes some time.
Yes, rolling circle quite
Time consuming.
Yes, quite time consuming, so it takes some time to be performed. Of course, if you don't want to wait, we can just skip to abort preprocessing and nothing happens.
I see. Okay.
For faster showing, we can disable background correction and show
Smoothing.
smoothing. For example, 100 is enough to.
Okay. It's way faster.
It's very fast.
And it is smooth now.
Yes.
Yeah, it looks like smooth. Good. And normalization as well. Normalization, the same story as for spectra.
Yeah.
Should we try any?
Yes. Why not?
Or maybe Z score this time?
As you wish.
Okay.
You can see.
Ooh. That looks different.
Yes.
Ooh. Wow. It tells me that maybe I should know what I do. But maybe we can apply some other normalization type.
Yes, we can play with
This
it.
one. I prefer the old one without normalization.
So we can unnecessary maps we can delete just by selecting them in the tab and pressing the delete button.
That's a good idea. This one and this one,
Yes.
and delete.
Delete, yes.
Delete. This is a good one. I like this one. Okay. So now it looks good. We are done with that. Analyzes. PCA. How many components are here? Let's try. Wave number. Number of components, you would say maybe 3 or 4.
Yeah.
3 or 4. What is this PCA technique?
Yes, the fastest technique is Nepal's algorithm. It is based on alternatively squares.
Okay.
There are other techniques, is Gram-Schmidt procedure of orthogonalization and singular value decomposition. Singular value decomposition is the most exact technique, but it is more time consuming. So for our needs, Nepal's algorithm fits well.
Tolerance.
It's good tolerance. It's 10 over -6.
Yeah.
So it is good.
Mean center.
Yeah, we can mean center our data because non-center data, the first PC would be will be just the average spectrum.
And we won't avoid that.
Yeah.
Okay, then okay. Wow. Now I guess first, in order to see it normal, we should change the dimension XY.
And you see principal components
Yes.
contains
1, 2, 3, 4. Yeah.
So as we can see, it is the first principal loading contains negative values, but we can.
Wow, how you did that?
Because our score map contains negative values as well.
I see.
So we can invert it. As you can see, the major contribution is from polystyrene.
Definitely.
Yes, because the major components looks like noise.
And how about calcium fluoride, the substrate?
It seems like substrate was eliminated after mid-century.
I see. Should we try something to see it actually? Change the settings. Let's say we go for the original file, analyze this PCA, and do the same just without mean center. Y. X. Number 1 component. Here it is. Number 3, that's more or less noise. But I also like that here, let's say the constant presence of the luminescence lamps, which are in this room, they were placed here. And that's interesting. But very nice spectrum of calcium fluoride, I would say, 3000 something. And the interesting thing that it is actually maximized inside the polystyrene bead. That's a little bit unclear for me. I was expecting an opposite situation. But this one looks opposite.
Because PCA show about variance. It is not real spectrum, it is some unknown linear combination. To resolve such contribution, we can play with non-negative matrix factorization, multivariate resolution, and so on.
This one?
Yes.
We should do that. 1, 2, 3, 4?
I think as we see that the fourth component looks like noise, we can
even 3.
Even 3, yeah.
Okay. Simplisma and NLS or MCR?
MCR.
Okay. What is the difference?
The difference is Simplisma and NLS we determine the pure spectra and do non-negatively squares. So pure spectra are the spectra at certain pixels.
Yes.
If we don't have pixels with pure pixels, with
but we have.
Yes, it works. Another case, MCRLS, it is iterative technique. It may improve our results. So we can play with both and see the difference.
MCI is model 3, we run it first.
Yes.
Okay. It takes time or?
Yes, it takes time because...
And it's done.
Yeah.
And it's all positive, I like it. So Y, X wave number. And this is PC1, basically. 2. Nice. 3. Spectrum looks weird.
It is weird because it is just...
Okay. Okay, I should click.
The same story.
But this is true. I like this result much more because presence of calcium fluoride is outside the polystyrene.
So we can decrease the number of components for 2 components.
Yes.
Because the third component also looks like noisy.
Agree with you. Good, but the original idea is done. We managed to subtract physical, yes. And as far as I understand, if you want to use the non-negative least squares, I click here, and this is a spectrum of calcium fluoride. I save it as library, and we use it for decomposition. And I also click for the maximum of polystyrene, save it in library, and we use it for non-negative decomposition, which would be an NMF, this method. Yeah,
actually this method automatically
selects the
most different spectra.
Should we try it?
Of course.
Also 50 iterations?
It would be just 1 iteration because we do not improve spectra.
3 components?
I think 2 components is enough.
2 components, okay. Okay, Y, X, wave number. And yeah, it looks valid. So this is actually maximum where there are no bits, and component number 2 opposite. I really like this result. But the difference between MCI is that spectra are way more noisy associated to the map.
Because spectra, in this case, the obtained spectra are just raw spectra. MCR updates spectra iteratively, so they looks
way better. Yeah, it's an excellent as denoising from my understanding. Look at this polystyrene spectrum. We never measured it in a map like that, but software managed to do it greatly.
Yeah, so it is the main difference between MCR and
NNF, MF, non-negative least squares.
Yes.
Nice. I guess And yes, all of this data we now can save. We save this image as a result, save spectra, we select spectrum, right click, save selected as txt. We can save image as here or through the file and export. Let's say we would like to save something we select here, this map, the final, the last one, in the format of MiraSpec viewer. And this would be MR Spectra or MATLAB. The same way. And then we can open it here to show or continue post-processing.
Yes.
Very nice. And as we can see, there is still a laser on a sample, and we can still see the presence of calcium fluoride. I think it's a good idea just quickly show something we can do with the spectra acquisition. First of all, we go to laser parameters. We can do it like that and show a little bit more. I can hide this one and get a little bit more space for spectrum. So first of all, we can increase the exposure time. Instead of 150 seconds, 1.5 seconds. And our peak is proportionally higher. Another option, I can increase the laser power. Now it's 20 milliwatts. Let's go for 50 milliwatts. Press OK, and the spectrum is accordingly more intense. How to save the spectrum? Right click on it, save selected, and it will be saved as TSV, the live, or you can also capture the spectrum. Let's say 10 repetitions. And this is an exposure time, and we keep gain 0. We press capture. And if I zoom here, you can see the gray spectrum. That is an average result over 10 repetitions. And when it's getting green, it's ready to be saved. And it's way less noisy. If we go here, the noise level is less after 10 averages. And we go File, Save. Let's save it, calcium fluoride. And just to show everyone how it looks, where was it saved? Here, calcium fluoride data. Double click on it, and it will be opened in Excel. TSV is a text format, so it can be opened, I guess, in any text reductor.
Yes, it tab separates values.
There is a metadata, serial number of the system, laser wavelengths, let's extend, laser exposure time in milliseconds, gain, laser current, laser power, calibrated on a sample actual power, and then 2 columns, Raman shift and Raman intensity. That's how it looks. Sorry. And now, in order to enjoy a little bit more of that, I would love to move on polystyrene. Step by step, tick, 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 tick. And we can capture the spectrum of polystyrene together with presence of calcium fluoride. But unfortunately, we were unlucky and it's burned. And we can see the result, how it is burned in real life. It's simply because 50 milliwatts at 50x magnification objective is too much. We should go back to 20. And select another grain. So now you can see already just fluorescence of something carbonized. So let's select another grain here. And probably in order to get a strongest signal, we should get a little bit on focus, like that. Sorry. And we should not forget that it's a cropped image. So the real is here. Is it burned again? No, this is the one. Okay, then we capture. Yes, as you can see, 20 milliwatt is enough to collect a nice quality spectrum. And we collect it somewhere here. Here we are. This would be it for today. Thank you everyone for your attention, and I hope today's time was useful and will be useful for our new users, for people who help us with selling these nice machines, and should be very helpful for potential new customers and everyone who likes Raman spectroscopy and Raman microscopy. Thanks a lot. See you next time.
See you.